Hi, my name is Mohammad Zadeh. I'm Chief Product Officer at ETAP. As the global power sector rapidly transitions towards sustainable energy, the importance of grid interconnection studies becomes paramount. Grid interconnection requirements, or codes, are technical specifications which define the parameters that a facility connected to a public electric network must meet to ensure safe, secure, and optimal operations of the electric system. The facility can be a power generation plant, solar farm, wind farm, or any other grid-connected source. A typical grid interconnection standard or code addresses various aspects of power plant performance. A comprehensive study that covers various aspects of the power plant operation, such as normal operation, fault, dynamic, harmonic, and transient response, is required to ensure that the interconnecting power plant complies with all required specifications. Standards and codes related to interconnections of renewable power plants and systems define many requirements, both at the points of interface and common coupling of individual inverter-based resources, known as IBRs. These standards cover various performance requirements, including but not limited to voltage and frequency write-through, active power control, reactive power control, dynamic active power support under abnormal frequency conditions, dynamic voltage support under abnormal voltage conditions, power quality, negative sequence current injections, and system protection. Learning and manually checking the compliance for each requirement against these standards or codes requires lots of skills and time. For instance, in case of reactive power capability requirements, it is essential to run hundreds of load flow studies and compile their results, considering many operating limitations of the assets within the power plant to determine overall power plant reactive power capability and grid code compliance. In addition, a manual grid code compliance study is prone to human error or misinterpretations of the standard. ETAP combines extensive modeling capabilities with advanced solution algorithms, enabling you to undertake the wide range of studies required for grid connections and grid impact analysis of wind parks, PV generations, and other renewable energy power plants. Various study modules in ETAP enable conductions of all required interconnection studies, including but not limited to load flow, short circuit, protective device coordination, transient stability, unified dynamics and protection, harmonic analysis, as well as co-simulations with electromagnetic transient programs known as EMT. In addition, ETAP offers 3 dedicated modules for grid interconnection studies: grid code harmonics, grid code load flow, and grid code transient stability. Also provided is a smart inverter element that handles all the required smart inverter functionalities required in different standards, especially IEEE 1547. Besides all of this, ETAP also offers a power plant controller and its digital twin that makes it very reliable and easy for engineers to evaluate power plant dynamic performance. There's much more on these specific solutions on the ETAP website to learn about. In this demonstration, we will focus on the ETAP 2024 major enhancements for reactive power capability analysis. In the ETAP Capability and Control Rulebook, you can find many international grid code rules, and ETAP is continuously adding to these rulebooks to cover more regions. Users can also add their own rules to the rulebook. First, let's look at the British Engineering Recommendation G99-2021 that is part of the Distribution Operation Code. There are 4 pages for PQ, QV, PV, and pHz profiles. This standard only has a capability curve for PQ and QV profiles. In the case of the PQ profile, this rule defines the required reactive power capability at different active power values. And for QV curve, this rule defines the required power factor capability at different voltage levels. A rule such as this one can be selected in the ETAP study case to check that the power plant complies against this grid code rule. Also in the ETAP capability and control rulebook, you can find typical equipment capability rules. Let's look at the typical 1630 kilowatt inverter. This rule allows user to enter the reactive power capability curve in the form of P versus Q or P versus power factor at different voltage levels. User can select to extrapolate the curve if the operating voltage falls outside the user-defined range. For each project, user should enter the equipment capability curve based on the data sheets or information they receive from their inverter vendor. For WTG, AC PV array, and inverter elements, user can select an equipment capability curve defined in the rulebook as megawatt limits. Power priority, including active and reactive power priority, can be selected. Both the rulebook selections and power priority can be optionally set globally in the study case to save time and avoid their assignments one at a time. Typical renewable power plants, including many IBRs, their step-up transformer, collector cables, the plant transformer, and possibly additional reactive power resources such as capacitor banks or STATCOMs. Furthermore, user must define the plant point of measurements where grid code requirements are applied. ETAP 2024 offers a new user interface, significantly simplifying renewable interconnection studies. With the magic of the power plant editor, user can select the plant energy resources and its points of measurement with just a few clicks. Additionally, user can define all power plants within their network with ease. Rated power can be calculated automatically or it can be user-defined, and selection options based on zone, area, and regions are available to quickly select power plant energy resources. In this example, as you see, the selected power plant has 16 PV arrays, 2 STATCOMs, and 18 wind turbine generators. The total rating is 77 megawatt. The meter POM meter is selected to define the point of measurement. In ETAP 2024, all grid code and renewable-related modules are grouped under the Renewable Study Group in the new ribbon bar user interface to provide easy access for performing grid interconnection studies. For reactive power capability analysis, select the load flow grid code mode. Prior to ETAP 2024, the Grid Code Analyzer controller was used to perform reactive power capability analysis. In ETAP 2024, the Grid Code Analyzer controller has been replaced with a study case options that significantly simplifies and accelerate a study setup and multiple type of scenario generation. In the grid code page of the study case, select the grid code capability rule with which compliance is required, and then select the power plant to study from the power plants defined in the power plant editor. The reactive power capability curve can be globally assigned to the IBRs of the selected power plant or the entire system. Power dispatch priority, active or reactive, can be globally assigned to the selected power plant IBRs or the entire network. PQ and VQ sweep active power and voltage range, and resolution can be adjusted as needed. The capability sweeping algorithm has been enhanced in ETAP 2024 to consider possible operating and design violation. Additionally, you can choose to avoid or ignore any critical or marginal alerts, such as overload and over and under voltage as defined in the alert page. Most default values for sweeping are good for typical studies, and with the few adjusted settings, users are ready to perform the Greek code analysis. Now let's run a Greek code load flow for this power plant. ETAP will run many load flows sweeping active power, reactive power, and voltage, and calculate P and Q at the power plant point of measurement. Once analysis is completed, a comprehensive Excel report will be generated. This Excel report contains project information, specific study case settings for Greek code load flow analysis, device capability rules used for power plant IBRs, detailed information of all device capability rules used in the analysis, detailed information of applied Greek code PQ and VQ or V power factor capability rule, PQ sweep table and charts for the studied voltage set points, VQ V power factor sweep table and charts for the studied voltage set points. The report helps user easily determine compliance with the selected Greek code capability requirements. As you can see here, the Greek code is not compliant as the Greek code required capability curve fails to fall within the power plant capability curve. In other words, the plant is less reactive power capable than it's supposed to be. For the case that we ran, as the Greek code capability rule indicates, the Greek code capability requirements were not met. Now let's change the configuration and connect two 8 MW STATCOM to the system and rerun the analysis. In this case, as you see, the Greek code capability curves falls within the power plant capability curve for all voltage power set points 95%, 100%, and 105%, and all the active power set points 15% and 100%. In fact, this study not only checks compliance against the Greek code, but also provides an essential method for sizing reactive power resources in the power plant, such as capacitor bank or STATCOMs, to meet Greek code reactive power capability requirements. In ETAP 2024, the report manager now supports Greek code capability analysis. This added feature means that user can generate Excel reports without the need to rerun the analysis. This is a great advantage as it allows the use of the scenario wizard as a placeholder to maintain study information without needing to separately relate the output database file name to the Excel report file name. For instance, if we would like to regenerate the report for the case that the STATCOM were disconnected, we can simply load the corresponding scenario and generate its reports from Report Manager, Results, Greek code capability report. Besides significant enhancement in the user interface of Greek code load flow in ETAP 2024, the sweeping algorithm has been altered to avoid operating constraints defined in the alert page of the study case, such as equipment overload or over or under voltage conditions. With this new algorithm, user can compute the capability curve at the power plant point of measurement without violating any alerts. Let's look at the same example, assuming that alerts are not considered. Comparing the PQ curves of both cases, it is clear that the power plant is less capable if it's not supposed to violate the user-defined operating constraints as defined in the study case alert page. In addition, the capability curves are calculated for all possible alert selections as shown in tabular format in the Excel reports in detail. This helps users determine which assets as part of the system play a role in limiting the capability curve, while only the selected violation option selected in the study case is used to generate PQ and VQ charts in the Excel report. For instance, in the case of PQ curve for 95% voltage set point, StatCom will overload if POM voltage is at the 95%, and StatCom tries to absorb reactive power that results in lower voltage at the StatCom terminal voltage as well as current increase beyond StatCom overloading capability. ETAP reports the possible operating points excluding all alerts and only critical alerts for user consideration. In the case of PQ curve for 105% voltage set point, only the planned transformer gets overloaded for the cases 15 to 18 where the plant is absorbing a large reactive power while generating a large active power. Another important alerting feature is that all planned assets can be automatically considered through settings Consider all planned devices in the violation section. If preferred, the power plant device alerts can be customized as before by selecting elements for plotting. If a renewable power plant has an energy storage system, the active and reactive power dispatch of the energy storage typically depends on the application. The ETAP grid code load flow analysis by default does not sweep the energy storage, active and reactive power, and utilizes the settings defined by the user in the energy storage editor. However, you can choose to instead sweep the energy storage, active and reactive power in the same proportion as other devices by enabling energy storage dispatch within the study case. As mentioned throughout this presentation, ETAP 2024 grid code load flow offers significant enhancement to speed up study setup and enable users to generate reactive power capability in a matter of few clicks. Another new feature towards this goal is automatic voltage range selection for PQ and VQ sweep. If the grid code has a voltage reactive power requirement, the minimum and maximum voltage of the voltage reactive power curve can be used automatically as a voltage range within PQ and VQ sweeps. Users have the option to manually define the minimum and maximum switch voltage as well. Let's summarize this talk. The manual analysis of grid codes can be time-consuming. For a simple reactive power capability compliance study, many scenarios need to be generated, and all results need to be compiled to determine PQ and VQ curves at the point of measurements of the power plant. ETAP offers a dedicated module that automatically sweeps active power, reactive power, and voltage as per the grid code that is stored in the ETAP rulebook to generate a comprehensive grid code capability report that can be directly submitted to the system operator. In the ETAP Capability and Control Rulebook, you can find many international grid code rules, and ETAP is continuously adding to the rulebook to cover more regions. This saves lots of time for users to fully comprehend the standards or grid codes and manually check the compliance against them. Users can also add their own rulebook. ETAP grid code load flow analysis can record and avoid operating constraints through alert settings to ensure that required reactive capability can be achieved without imposing any overload or over and under voltage conditions. ETAP grid code load flow is one of the many modules and solutions that are offered for grid code studies. You can explore our website to find other products such as grid code transient stability, grid code harmonics, and power plant controller. Thank you for joining us today.